Welcome back. In the previous lecture we discussed many types of PV systems. In this video we will look more closely at each component of the system. The learning objectives of this video are to understand the importance and the role of the various components forming a PV system, such as PV modules, the balance of systems and the outputs. Here we report the topology of a generic standalone system with storage for powering both AC and DC loads. Although the solar panels are the heart of a PV system, many other components are required for a working system. Let's divide these components into three main groups. In blue we have the PV panels and in general all the components generating power. Then, in red, we have all the other devices required for a working system, which are called the balance of systems, or BOS. Finally, there are the loads, which can require direct or alternating currents. In the same way, we can divide the components of a grid-connected PV system in several groups. Again, we have PV panels at the generation side, then the balance of system, which is much simpler than in the previous case, and finally the outputs, which are the AC loads and the electricity grid. Here, all the components required by a PV system are summarized. In addition to the previous slides, we have the bypass diodes that are part of the PV panel. We have cables and mounting frames in the balance of systems. Which components are required depends on whether the system is connected to the electricity grid or is designed as a stand-alone system. So let's get familiar with these components. We start with the generation part of the PV system, which are the PV modules. The task of a PV module or solar cell is to generate electricity. Using a single solar cell, however, is not practical for most applications. This is because a single solar cell delivers a limited amount of power under fixed current and voltage conditions. In order to use solar electricity in practice, a number of solar cells have to be connected together to form a solar module or PV module. As discussed in the second part of this MOOC series on photovoltaic technologies, there are multiple technologies available on the market. These technologies can roughly be divided in two groups, namely the wafer-based crystalline silicon modules and the thin film PV technologies. They involve different ways on how to connect the cells together. Nowadays, wafer-based crystalline silicon PV modules occupy about 95% of the market globally, while the rest of it is occupied by the thin film PV modules. Of course, they have different market purposes. Thin film modules can be made flexible and are therefore suitable for niche markets related to building integrated photovoltaic or more generally for environmental integrated photovoltaics. After solar cells have been connected together, modules are formed by encapsulating the cells with different materials. The encapsulant is added to protect the cells from environmental influences. Finally, concerning large-scale generation of solar electricity, multiple PV modules are combined to form an array. In many modules, there are two other important components. The first is the bypass diode, usually placed in the junction box of the module. It protects solar cells to avoid overheating of these solar cells, often also called hotspots. The second is blocking diode, which prevents the current from flowing from the external circuit into the PV module. So, which are the components making up the balance of systems? Here we have the mounting structure that mechanically fixes the modules and arranges them towards the sun with optimal tilt angle. Then there are cables that are used to connect the different components of the PV system to each other and to the electrical load. It is important to choose cables of sufficient thickness in order to minimize the resistive losses. Storage devices like batteries are instrumental in stand-alone systems. The batteries provide a reliable source of power. As long as they are well maintained, they assure that the loads receive needed power during the night and in periods of bad weather. However, the balance of system components do have some drawbacks. When adding a component, the efficiency of the PV system decreases. This applies also for batteries, since they exhibit some thermal and chemical losses. In addition, they have to be replaced more often than other electrical components in your system. So when you want to have a PV system with storage, you have to take that into account. The PV modules are characterized by a certain lifetime, usually 25 up to 35 guaranteed years. The batteries, however, have a much shorter lifetime. Its lifetimes are currently guaranteed for at least 10 years. On the market there are many types of batteries, but for PV applications often the lithium-ion batteries are being used. Equally important to consider is the economic impact on the overall system expenses. When you need a lightweight system or high storage capacity, the use of the lithium-ion technology is preferable but also more expensive. Lastly, it is also important to account for safety regarding thermal control and health concerns on the chemistry employed. Then we have power electronics in PV system, conditioning power flow from the PV array to the rest of the system. DC-DC converters change the PV module output. Depending on the time of the day, on the weather conditions and on the connected loads, PV modules might work at voltages far from optimal. The DC-DC converter applies a suitable voltage to the PV modules for maximal power transfer to the load. DC-AC converters, also known as inverters, are used in grid-connected systems. The inverters convert the DC electricity coming from the PV modules into a sine-based AC electricity form that can be fed into the grid after supplying the loads. Of course, we have also stand-alone inverters that just change the DC power coming from the module to AC power that is delivered to a certain AC load. Both types of inverters are characterized by high conversion efficiencies of between 96 up to 98%, depending on the working conditions and on their embodiments. Furthermore, inverters can contain an additional board in their circuitry for activating a maximum power point tracking strategy. As a result, the PV module can operate at the maximum power point voltage. As a matter of fact, many inverters have embedded a DC-DC converter to change the variable voltage of the PV array to a constant voltage that is the input for the actual DC-AC converter. We will discuss maximum power point tracking in more detail later in this course. Finally, the charge controller is used in PV systems to control charging and discharging of the battery. The charge controller is a 3-port terminal. On one port you plug the PV panels, on the other load, and on the third the batteries. Some models of charge controllers contain also a DC-DC converter alongside a maximum power point tracker. This is added to decouple the voltage and the current of the PV modules from the voltage and the current of the battery bank. In this way we can always obtain the maximum power from the modules. Though not part of the PV system itself, the outputs have to be taken into account during the design phase. Outputs include all the connected electric appliances and the grid. They must be considered in terms of required voltage level, power consumption in case of loads, and AC or DC current. In the second week, we will discuss the electricity network, the grid, and the role of PV in the future electricity grid as well. In this video, I have given a brief overview of the components forming a PV system, such as the PV modules, the components making the balance of systems, and the outputs. We will discuss these components in great detail in the video lectures of week 1 and 2 of the third part of this Solar Energy MOOC series. In the next 3 video lectures, we will discuss PV modules, so see you in the next video.